Good morning, everyone, and thank you for joining us for today's session in the Empathic Computing and Beyond Seminar Series. My name is Kunal Gupta, and I'm thrilled to welcome you all to what promises to be a fascinating discussion on adaptive mixed reality systems and how technology can better understand and respond to us. It's my absolute pleasure to introduce today's speaker, Dr. Francesco Chiossi, a senior researcher in the Media Informatics group at LMU Munich. Francesco has a diverse and rich academic background with strong expertise spanning cognitive neuroscience, human-computer interaction, and multimodal computing. His research focuses on using implicit measures of human behavior, such as electrodermal activity or EDA and EEG, to design adaptive systems that can intelligently respond to user needs. Dr. Chiossi's work also looks into informing AI systems of user states, enhancing collaboration with intelligent systems, and enabling robots and other technologies to better understand and respond to human intent. His vision bridges neuroscience, AI, and HCI, offering innovative insights for designing bioadaptive systems. In today's talk titled Enhancing Mixed Reality Through Adaptive Interactions, Francesco will explore how mixed reality technologies can dynamically adjust digital content using multimodal insights, such as physiological signals to optimize engagement, reduce cognitive strain, and support seamless interaction. He'll also share his work on embedding unobtrusive sensors into mixed reality hardware and how this enables intelligent systems to better align with user goals and states. We are truly fortunate to have Francesco here with us today, and I'm sure his work will inspire thought-provoking discussions. Without further ado, please join me in welcoming Dr. Francesco Chiossi. Francesco, the floor is yours.
Thank you very much, Kunal. It's a very kind introduction, and for me, it's an honor. It's my first talk as Dr. Francesco, so I'm very happy to be here, and thank you and Professor Mark Billingus for inviting me. It's a very nice welcome environment. I'm happy to invite you to my talk as well. So today I'm very happy to talk to you about my most recent work and talking about how we can actually embed and make mixed reality intelligent through adaptive interaction. So imagine now that you are wearing your mixed reality headset and you just arrive at your office. The office is kind of alive and bustling. There is constant noise, flashing lights. People are moving all around you. The environment is kind of overwhelming. So you keep trying to focus on your first task on the day, sipping your coffee, but distractions keep coming. And now imagine you can actually wear your mixed reality device. And suddenly, all of a sudden, all that chaos fades out into the background. You're left alone with only things that matter, important and tailored for you. So there is no need to take out your smartphone or break your focus. The device is context aware and uses physiological sensors to tune in your mental state. So now, from a state of being overwhelmed and distracted, it dials down the complexity of your surroundings. And if you're focusing on a task, you are shielded from unnecessary distraction, helping you to stay grounded. So this is my vision, and I believe that mixed reality can transform how we are entertained, learn, and consume digital information. But before actually we start coming through my research, I would like to start with some quick definition that I believe you are already kind of familiar with to set my research into perspective. So this is the mixed reality continuum. We follow this taxonomy that basically creates a gradient of a progressively increasing virtuality in the environment. So on the left, we have the real environment. And then, for example, like here, you see in the video of the MetaQuest demo, we have augmented reality. So here we have a virtual object, digital object on top of our physical surroundings. Then we have augmented virtuality. So here we see a predominance of digital information around us, where there is overlaid information that is also grounded in our physical environment. This is often used, for example, to keep a spatial or social awareness of the people around you and objects, to avoid, for example, dangerous occlusion, and also to keep us aware of our surroundings, for example, also show social awareness. And then we move into the virtual environment. Here we have a complete display the virtual environment here. We are interacting and we are perceiving a digital space which blocks us out from the real world and replaces it with a virtual one. And sometimes this is also actually enhanced through audio and touch or haptics stimuli. But now let's think how we actually can interact in such environment. A lot of this starts with the observation that when we compare the interaction with like the one on the left, which is actually my desk where I'm actually today now, and 3D ones like on the right, when we compare them, we see a lot of challenges from the HCI perspective that we can put together designers, developers, and researchers. So 2D interfaces are great. They are always in reach. You can drag a window somewhere, pick up your smartphone, and this is not relevant where they use because you can do it on the go, on the subway, or on stage while giving a presentation, for example. But when we move to 3D, the mixed reality space, we can potentially display content everywhere. We can design interface that picks all the space around us. And here the space matters because it could be distracting or could even impair the way we are interacting. Imagine occlusion behavior, or occlusion problems, for example. So such interfaces that will be embedded in our reality, not only when we sit like here, but also when we're gonna envision ourselves on the go, on the subway again, or on stage. And this will be incredibly impactful in how we're gonna work and in general, how we're gonna behave, how we're gonna process information in the environment as well. So we want though to avoid those scenarios like this one when we have something that can actually influence us. So when we are overwhelmed by both physical and virtual information. This, of course, it's an exaggeration, it's a doomsday scenario, but to a minor extent, we have to acknowledge that there is a risk that augmenting environments is not only challenging for designers, but also challenging for users now. Because when we add on top our physical awareness or a physical task, a whole new digital world that is not aware of the physical one, then we create a totally sensory, cognitive, and also emotional overwhelming for the user. So then how do we improve interactions with interfaces that are static in design, but serves users that are dynamic and always changing? Currently, traditional fixed interfaces might not be enough to handle those complex real-world settings when we are interacting with digital and physical information. We continuously shift our focus, adapt to new information, and change our intention. So then how can we create systems that can adapt to the users that are evolving in real time? How we can support stability, relevance, and systematically adapt the static content? Well, my answer here, it's clear, it's simple, is that the future of mixed reality is adaptive. So those systems, adaptive mixed reality systems, are actually built on three core components. The sensing component that captures data from the user and the environment, and this can include physiological data, like heart rate, eye movements, and as well as contextual information from the environment. The interaction component that actually allows users to engage with the digital content and where we can actually incorporate dynamic and context-aware interaction that can actually allow users to manipulate and respond to the mixed reality environment around us. And last, the system component where all the pre-processing and the intelligence comes together. So here, data are pre-processed and allow the adaptation of the content in real time based on user needs, attention, or engagement in my case. So based on this, I developed 3 research questions in my presentation and in my work that are driving my work, which is how actually do users allocate attention and how this attentional state actually can fluctuate across the mixed reality continuum. How can we actually support their performance by considering the physiological or implicit correlates of attention in a, for example, VR adaptive system in my case? And last, can we actually embed physiological sensing in mixed reality and design those embedded systems for reliable signal acquisition and validity? So let's kick in with the first part of my talk. I investigated various topics, but today we're gonna focus on mixed reality. So we're gonna ask if the blending of virtual and physical objects can actually impact our attention allocation. So let's start first with some background here again. So here there is a lot of work that studied actually how we allocate our attention across the mixed reality continuum. So for example, here Van de Over at ISMA in 2022 actually studied compare virtual and physical objects. So physical objects that were searched in the real environment, and they actually found that users were slower in VR, but similar accuracy and perceived workload. Then we move to AR only, and here Kim explores visual search tasks in outdoor environment and found that, for example, the objects were more salient when they were virtual compared to physical ones, even in low light conditions. And again, David John actually found that it's possible to predict the saliency of objects in VR using only gaze behavior features. So what we see actually now that we have a lack of exploration of objects or interaction that share both virtual and physical information at the same time. So here I want to talk to you about a paper that I presented this year at ISMAR that is going to talk about how we can identify virtual and physical information in mixed reality. So here we had 2x2 design. So basically we presented participants and asked participants to identify objects that were either physical or virtual. And we presented those objects either in augmented reality or in augmented virtuality. So if you remember what I said before, basically the surrounding of the environment was either completely physical in the case of augmented reality or completely virtual, as in the case of augmented virtuality. So this is the structure of the experiment. So basically we did a trial-based structure. So we basically provided a fixation cross to the participants, as you can see here, and then they had 5 seconds to identify an object placed on a shelf, and then there was 1 second when the environment was empty to allow for attentional refresh. And those are the objects that we presented. So on the left, you can see the objects in augmented virtuality. So the shells is actually virtual, but we placed a shader and presented the users virtual and physical objects. When we actually go to AR, we see that the shells are actually physical, but there is also, again, here a blend of virtual objects like this one or physical objects. So this is actually how it looked like in AR. So this is basically we rendered a video of a physical room in our institution here in Munich, and we asked the participants to identify an object. So here we have the 1 second plus jitter fixation cross, then we have the fixation cross. So we asked the participant to identify, in this case, a red pyramid. We didn't provide an image in order to avoid specific learning effects or to not bias the participant, and then we show them a physical target here, for example. Here we have also here the purple sphere. This is a virtual object, actually, as you see. And the participant is correct and selected. And here it's how it looked like in augmented virtuality. So here the environment is a 3D rendering of the other room. We try to mimic the lighting. We chose the same color by color picking and so on. So here the environment is pretty similar. It's just completely virtual, and we are only showing physical objects in augmented virtuality. So we can jump to the results and we have a look at it. So what we found for the behavioral results here is that participants showed a similar accuracy across AR and AV conditions. So they were similarly accurate in identifying the target, but missed, for example, more virtual targets in augmented reality. So basically they were spending too much time, more than 5 seconds, in finding the AR virtual targets. While instead, augmented virtuality led actually to faster reaction times and fewer misses, particularly for virtual objects, indicating that there was a better search efficiency in AV. Then we can move to the eye checking results. So here we measured eye checking results as a measure of their gaze efficiency, and we found that the participant had less fixation and less saccades in augmented virtuality, especially when the targets were actually virtual. Then, if you remember, we had trial-based structure. So here we measure the brain potential, time locked to the presentation of the video search onset. And this allowed us to measure the distractor positivity. You see, it's a brain wave that is positive after around 500, 600 milliseconds, and basically measure the capacity of the participants to suppress irrelevant information. And here we found that basically in AR, the distractor positivity was diminished, and basically it means that the brain can filter out distractions and focus on targets better in augmented virtuality compared to augmented reality. And this is the boxes of the significant results. So, and last, we also evaluated a bit the perceived workload of the participant. And here we also found that AR actually showed a higher workload, participant reported higher workload in AR compared to AB as well. So what do all those results mean? Like, what can we kind of put, how can we put things together? So first of all, we can say that the attention allocation of the user, how can they identify relevant information and filter out what is not relevant, actually shifts across the continuum. Environments with virtual information have a predominance, basically with the predominant virtual information actually diminish the cognitive load and actually support improved search efficiency compared to AR environments. And last, we found that virtual objects are easy to identify, supporting the information processing of the user, where instead we found the opposite for physical objects, that showed more misses and higher cognitive demands. So now that we know that attention is changing and we are aware of different user state, the question is, how can we actually design an adaptive system that can support user in identifying what is relevant for them? So here, across the various research questions in my work, we're going to talk about how can we design an adaptive system based on EG data that can support attention allocation. So here we switch from a perspective where we want use physiological data for evaluation, as I did before, so we want basically to understand how users are interacting in mixed reality, to a perspective where actually the physiological data are employed as an implicit input for a system to understand the user state and actually support and adapt the environment or the task to achieve specific goal of the user. So here we're gonna use physiological data for understand and predict the behavior of the user, design an adaptive interface, and then ideally as an ultimate goal, we can support the performance of the user and its comfort. So now let's move to our use case. So maybe some of you are actually familiar with this game, but it's a game that actually well exemplifies how do we allocate attention in VR. So here we are focusing on a task, which is defeating the enemies. This requires top-down attention, but also we have to react to sudden stimuli or distractions. So for example, such as an enemy is appearing unexpectedly, and this recruits bottom-up attention. So to understand this, we actually can explore the bottom-up and top-down control of attention by Corbetta et al. So here, basically, we have two systems in this model. The top-down, that is basically goal-oriented and allows us to focus on tasks that are like everything that is relevant for us in the environment or our objective, for example. So in the context of VR, for example, when we are tracking an enemy or computing an objective, we have this top-down system that is active, and it directs our attention according to our goals. Then we have the bottom-up control system. That is a sort of circuit breaker. It's something that tries to break down the top-down and allocate our attention to unexpected or salient events. And here can be, for example, in VR, sudden movements, sounds, or new objects that are appearing suddenly in the environment. And basically, this system, the bottom-up, is actually useful from a biological perspective because it allows us to react to potentially important distractions, something that is new, something that is salient in the environment. And in a visually complex environment, such as can be in VR, but also in AR or augmented virtuality, we are constantly switching between those two modalities. Why this is relevant? Because each of those two systems actually can rely on two types of attention. So the top-down modality mostly focus on internal attention. So when we're actually planning, strategizing, and reflecting on something new, or external attention, when we're actually focusing on the external cues of the environment. For VR, those two types of attention actually is super important because bottom-up can relate to how we are, for example, activated by the external environment, how do we feel engaged and immersed with this environment, and how much we are spatially aware. On the other side, internal attention can relate to how we can actually manipulate information, so working or episodic memory, but also to mind wandering. So we are kind of distracted or immersed, for example, in meditation as well. So those two types of attention actually have two specific, very specific EG correlates. So when we compute the frequencies from the EG data, we can actually see that when you are in an internal attentional state, both alpha and theta frequencies are actually increasing. While when we are on an external state, we actually see that, as you see in those videos, both frequencies are actually decreasing. So you can already imagine that those two states have clear specific direction of EG correlates. So when we are aware of this, we actually know that we are never completely external or completely internal, especially when we are in virtual reality, for example. So since those two are in a continuum, the problem is not to be completely external or internal, but actually how to achieve an optimal balance between the two. So in this paper, I actually investigated how we can actually design an adaptive system that is attention aware. And let's have a look at what happened, like what was the impact on the user, and I can actually automatically detect the state, the attentional state of the user. So here we have 4 blocks, experimental blocks. So one was the adaptive system that was optimizing for external attention, and then we had another system that was actually optimizing for internal attention. And the other 2 blocks were either fully external or fully internal. I'm going to show you how they look like in a minute. And they were used as label for our classification task later. So this is the visual monitoring task. You're basically surrounded by distractors, and you have to basically follow the distractors, in this case, like a blue one, for example, with your gaze. So this requires you to engage with external cues. Then we have an end-back task. I guess some of you are familiar with this task. So it's a task that basically requires you to remember the color of this information and compare it with the color of the sphere presented next. So basically, this is a sort of interplay between internal attention, because you have to remember the color of the sphere, and also external attention, because you have also to compare your attention towards something external. And here, the decision rule is based on the matching of the color of the current sphere compared to the sphere presented two steps before. That's why it's called end-back 2. And this is instead the visual adaptive block. So here we are basically adapting the amount of distractors in the environment based on the variation in theta and alpha frequency. So basically we are adapting based on the internal or external state of the user. And one state, it's balancing for internal attention, in this case, accuracy is pretty low, or for external attention. Okay, so now we can move to the results. So here we compare performance, perceived workload, and we actually apply a classification task when I'm gonna follow up later. So here we actually found that the external system, so the system that was balancing for external attention actually resulted in decreased performance, but we found no differences in reaction times. Then coming to workload, we actually found that this drop in performance was actually matching an increased workload in external system compared to the internal system. And now in a follow-up paper, I actually investigated how we can automatically detect the tension, because in the previous paper I showed you the adaptation was performed in a route-based manner. So we were basically, it was a system that we designed after multiple trials, seeing how the impact of the preprocessing pipeline was impacting the change. So what we did here instead was that we used we inspected 20 time windows of the EEG data. We extracted the frequency, all of them, alpha, beta, theta, gamma, and beta. And then we trained different models to see how they were actually performing in terms of accuracy. And basically, we compared the amount of data based on the windows and the feature sets. So here, for the feature sets, we actually found that consistently, we had a set of features that were actually overperforming all the other combinations across all the models. I'm not gonna read them all for easiness, but like basically we always found the same 8 features that were supporting the highest accuracy, at least at 80% of accuracy across LDA, support vector machine, random forest, and neural network. And then we also did a time window analysis using Bayesian mixed models, and we actually found, and this is not very surprising, that the bigger the time window, the bigger the accuracy in the classifier. And for this, we only used the top 8 models which train based on those features. Then the question was how, like, okay, sounds good. Like, I mean, we kind of expected that more time in the data, more samples leads to better accuracy, but like actually how much data we need to reach a kind of a plateau. And for this, we ran a piecewise regression. So basically we try on the accuracy. So basically we try to evaluate how much time you need in order to achieve the highest accuracy before it is a plateau. And this was actually pretty interesting because we found that all the models were kind of plateauing in a similar way around 6 seconds, LDA around 6.3 seconds, the SVM around 6.5, the neural network around 6, after dropping the performance. So, and this was actually way before the 20 seconds we used in the other experiment, in the other paper. So what can we actually put together here? So first of all, coming from the first, when we adapt a virtual environment and we adapt the surrounding visual complexity, we can actually support the user attention allocation, and this results actually in an improved task performance. Then, when we combine EEG frequency bands, we can actually have a very high classification accuracy using only EEG data, EEG frequency specifically. And we also found that you need, of course, more data help you in the classification task, but after breakpoint analysis, we actually found that around 6 seconds, 6 to 6.5 seconds time window is optimal for all models for detecting the attention allocation of the user. And this allows actually for real-time feasibility, allowing for a practical choice in adaptive VR systems. So this should be the next steps in research. So now we move from, so now that we now know that attention awareness actually is an important feature for supporting task performance, we are able to move on. And now the question is, how can we actually add attention awareness? How can we embed this into a mixed reality system? So now I'm happy to talk to you about SenseCon. It's a paper that I published at Mobile HCI, where we basically investigated the feasibility of adding multimodal physiological data analysis inside a VR controller. So here, this is me holding it. So basically what we did here is like we embedded a specific sensing system. This is for heart rate, and this is for EDA, for collecting physiological data that are embedded inside the controller. So here we had two research goals. First, we wanted to identify where to place the sensors. And then we wanted to be sure that no matter where we place the sensor, or like knowing where we place the sensors, we still want to deliver a high signal quality and good user experience, that basically the device is actually accepted by users. And for this, we designed 2 studies. So let's have a look at them. So first, we want to identify where we have the highest skin contact in a way that we can actually have less noise, higher signal quality, while still preserving user experience. So what we did was a kind of a thinking out of the box experiment. We asked the participant to hold the controller, and at the same time, they were actually getting their hands dirty with paint so that they could leave an ink, a trace of how they hold the controller. And then we actually took a measure of how they were actually overlapping across participants. So we basically took a picture and compared how they were overlapping the area of grasp. And what we found that participants were at the highest overlap across participants was on the right side of the controller with 87.1%. So this was the best candidate for placing sensor, because here we have a certainty of 87% that the participant will actually have contact with the skin there. So now that we know where to place the sensors, we decided to implement the system. And here we use ESPD D1 Mini to stream the data in a Wi-Fi network using established framework, the LSL framework, to stream both EDA and PPG data in a Wi-Fi network. Specifically, we chose the Groove GSR sensor because it allows for high sampling rate, up to actually 1000, but we're gonna see if it was actually the real sampling rate. And for this, we use copper foils. And then we implemented a pulse sensor, which is a commercial consumer grade PPG sensor, but this was actually adapted to actually acquire raw data and not the heart rate delivered from the signal, because we wanted actually to apply state-of-the-art pipeline to this. So now the question in study 2 is, can we actually allow a better UX when we actually embed sensing in a VR system? And second is, do those sensors allow for comparable signal quality to a medical grade device? So we compare the signal from SenseCon to a medical grade device. This is a device that is used both in clinical and in neuroscience applications. Kind of, you see, there is a good amount of wires here, so that was actually the burden of a medical grade device. And then we actually, in the experiment, we first asked the participant to familiarize, so then they rated the acceptability, the acceptance, and the usability of the system. And then across a series of standardized tasks, we actually evaluated the signals delivered by both devices, both systems, that were actually recorded at the same time. So first, we asked participants to sit and stand. So this is done to evaluate first physiological baseline, but also orthostatic settings under orthostatic stress, so like standing, for example. And then we actually designed a selection task. So here we wanted to evaluate the artifacts of moving hands and of the entire body. So we asked participants basically to collect a sphere with the right hand and a red cube with the left hand. Then we have the task you saw before, the end-back task. This is a high, so it's like mimicking a high workload task on the signal quality, of the signal. And then we have a Stroop task. This is a task that is popular for evaluating the effect of cognitive interference and cause of physiological stress. So here you have to select the word. So in this case, you have to click the yellow wall or the red wall. But in this case, interference because, of course, we have conflicting information coming from the color. Let's have a look at the results now. So in terms of acceptance and usability, our system, SenseCon, actually outperformed the medical grade device in all measures. So we were more open, they felt more also socially acceptable to use SenseCon compared to the other one in a VR setting and so on. Then coming to the signal accuracy, we actually found that SenseCon delivers for EDA around of 80 samples per second, so 80 hertz of sampling rate, while the PPG is a bit slower, kind of the half, around 40 samples per second. And then we actually compared EDA features, and we actually found that both EDA features, so slow and fast, so tonic and phasic EDA, are actually not different. But to further investigate the signal accuracy, we actually used blend-Altman analysis. It's a statistical method to assess basically the agreement between two different measurements techniques by plotting the difference between the measurement against their own average. So here are the results for skin conductance level, so the tonic component of EDA, and here you see that there is a proportional bias in most tasks. So this means that the difference between the system is actually relative to the size of the measurement. So here we found that generally SenseCon level are actually underestimating. So they are providing either lower values like here or extremely higher values. While for heart rate, you see that the lines here are kind of in parallel. So this means that there is no bias in the measurement, but there is actually more systematic error. So here we found that in general, to collect data from SenseCon, you need to add 7 beats per minute to your heart rate, and then the results are actually comparable to the ones of the medical grade device. So bringing us to the end of this third topic, what can we take away is that if we can design systems that are actually designed for optimizing the signal quality and the skin contact, we can actually provide valid and reliable results for embedded VR systems. And this also allows for improved comfort and usability without compromising the data quality of the data collected. And this can then be used for a peripheral physiological measure, supporting detection of user state based on those physiological data. So now let's wrap up and come through the results and what they can mean for future work. So we had those is the kind of the little journey I brought you through, from evaluating attention, designing attention awareness in the system, and how can we actually embed such signal into the system. So here in RQ1, we found that target processing is more efficient in augmented virtuality. It's easier to filter out information in AV, and this requires more resource in augmented reality. And this also results in lower mental effort and more structured search behavior in augmented virtuality. So this, for us, means that attention fluctuates across the continuum, and we can actually mitigate the information processing challenges posed by the physical environment with more virtuality in the environment. Then, coming to the second research question, we found that we can balance attention of the user by adapting the visual distractors in the surroundings and actually support task performance, but also we can also, on the same features that are correlates of attention allocation, actually design and have classifier that actually classifying attention allocation with high accuracy. And last, with the last paper I presented, we can actually embed physiological sensing into the mixed reality or virtual reality system, showing improved user experience compared to other signal acquisition methods, and provide an evaluation framework for sensing prototyping in mixed reality. So where can we go with those results? So I see that there are a series of, let's say, applications in my work, and those are sensor fusion, contextual state detection, and transitional interfaces. So first, for sensor fusion, we know that, or especially in my work, I investigated eye tracking as a measure of workload, but also of how to identify objects, so special attention, EEG for attention allocation measure, and EDA and heart rate or electrocardiogram for physiological arousal and mental stress. The point is that currently, those measures actually use separate, at least in my work. So the idea here is that we can move to contextual state detection based on a multimodality and sensor fusion. So again, here we can close the loop, but in an automated way. Because the approaches I use are rule-based. So they lack the flexibility and generalizability across tasks. So if we move towards context-aware machine learning, so we can, for example, fuse multimodal data together with, for example, computer vision, so we can basically merge the internal state of the user with what is actually in the external environment. We can actually empower and enlarge the application of intelligent mixed reality systems. So here, basically, we can also not only have, let's say, trait acquisition, so acquiring data that are only on that moment, but they can actually be expanded to the entire day, for example, and this gives also a larger and long time window on the user. And this would basically allow us to merge what is physical and digital in our reality. So, for example, let's give you an example of this. So let's imagine it's the end of your day and the desk is messy and it's time to go home. So basically the system actually is aware of the time of your day and can, for example, highlight information that is relevant for you. In this case, the keys for closing your office, opening your car, and driving home. And this brings us also to transitional interfaces. So interfaces that can basically merge the physical and digital world, because currently our physical and digital world, they are not in sync for sure. So imagine that you are want to go for groceries and you are collecting up your notes for the grocery you want to buy. Well, this can make you feel frustrated because you're basically trying to put together information from on your phone from your physical environment, and this creates demands on our attention. Or another case is like you're trying to assemble a new piece of furniture, and of course you have to check a YouTube video, how to assemble a specific object on the phone and so on. So basically this creates more workload, and it's hard to support you in time-sensitive tasks. So here, when we actually can merge physical and digital world, we can actually create a bridge and basically provide better support to users when they are actually trying to solve problems that are merging both worlds. So here you can see that, for example, with a mixed reality headset, you can basically display and create an online grocery list and highlight, for example, objects that are kind of where can they be placed, for example. And on the same side, you can have a design system that are redirecting your attention toward different parts of the environment so that you can focus your attention on what is relevant and not being confused, for example, by the multiple objects or tools that you have on your desk. And the idea so that we can actually use computers, virtual displays, to actually redirect our attention through physical and digital tasks. And with this, it concludes my presentation. I'm very happy to take any question, and I'm very grateful for you inviting me and for the conversation we're going to have. Thank you again.
Thank you so much, Francesco, for that truly insightful and thought-provoking presentation. And I'm like, it's incredible to see the application, the future work that you have sort of proposed over here. I'm sure today's talk has sparked plenty of ideas and questions among our audience. So now we'd like to open the floor for questions. Feel free to type your questions into the chat box or raise your hand or ask directly. If you prefer, you can also share your reflection and ask follow-up questions related to specific aspects of Francesco's presentation. So yeah, anyone have question? Yes, Gal.
Thank you, Francesco, for the very inspiring talk. I have a technical question regarding your first study, which you compared the VR, so to say, augmented virtuality and augmented reality environment. I noticed in the augmented reality case, the shelf was initially empty, and then suddenly you see the objects that is filled in, including physical objects. I was wondering if are you using a video see-through headset and you're placing physical objects on the fly, or how are you doing that you have
That's
an
a good
empty shell
question.
and suddenly, yeah.
Yeah, this was an amazing task. So basically what we did, so they disappear because we want to basically first have an attentional refresh. So the image is less cluttered and the participant is not doesn't get attentional fatigue. And then because we can display new things. How did we do this? So basically, for the augmented virtuality scene was fairly easy. Like what we did was that, oops. So here. We basically add a shader on the picture of the object. So basically we remove the background and we add only the objects, and we use a shader to display the object. So that was fairly easy. What was a bit more challenging was to actually place the objects in AR, because in augmented virtuality you can make appear, disappear the objects, but for this we actually display the video. So it was actually simulated video see-through. So basically we displayed everything inside an HTC Vive. And for this, we basically took a picture of the physical objects. And in this case, we took 200 pictures of different placements. So we uploaded a CSV file in Unity, and we kind of were aware of where every object placed, so X, Y, Z coordinates, so that we can actually connect with the eye tracking data. And then we displayed on top the virtual object. So it was a long job of taking many pictures, and we used a 4K camera, so we also ensured that the distance was always the same and placed at the same place of the participant. So try to avoid occlusions. That's why also we didn't place any objects on top and at the bottom, because it was easier for the user and for the camera to display the objects.
I see. Thank you very much for clarifying that. A follow-up question.
And if it's useful, we have everything actually open source. So if you also would just want to play with the environment and things, everything is at the end of the paper. We have all the materials open actually. Also
That's
scripts
great.
for analyzing the data.
Yeah, that's great. Thank you very much for opening that up to the community to reuse that. Thank you very much. A follow-up question I had was, so you found the difference between augmented virtuality and augmented reality in this study. The VR environment you modeled seems to be quite photorealistic, and you still finding a difference. What do you think is driving that difference? Is it still a visual fidelity, or is it psychological feeling of being in a different environment, or what do you think? What's driving the difference between the two?
That's a good question as well. I think that when we have physical objects, I mean, I also have them here on my desk. We have more complex path. Like the objects here the virtual ones are opaque, but still they are lacking a bit of the patterns of the original. So I think, and this actually plays an effect with the surroundings. So the virtual surroundings are more perceptually complex, less perceptually common in the augmented virtuality scenario. While in AR we have to a certain degree still shadows and patterns so I believe that like here the overall environment becomes perceptually more similar. So it's less distant, everything is similar, and this allows the physical objects to have higher saliency. And but this doesn't match the background. While in the augmented reality, we have a perceptually complex background, but visually simple and therefore more salient, I believe, virtual objects that allow for faster detection. So that's why I believe that like in the future, like we should have more virtuality to redirect your attention toward what is relevant. So to a certain degree, it can also be like, I'm struggling to find my wallet. You can make your wallet virtual in your VR mixed reality headset so that it becomes more salient, and then instead of having arrows, for example. I hope I didn't talk too much or was too long.
Thank you
Okay.
for that. Thank you.
Thank you. That's yeah. I mean that made the whole picture clear now. Thank you. So we have only 4 minutes left, but if you have some extra time, because I think there'll be more questions. So if you have extra time, we can extend the discussion. Francesco, is that okay?
Yeah.
Yeah.
Sure.
Okay. Perfect. Thank you. So Evan, you have a question.
Yeah. Thank you, Dr. Francesco. That's a really amazing presentation. So I actually really like the kind of the using scenarios that you put in the like a future section. So I'd like to ask like how do you think the adaptive mixed reality system could help when like people are in the task that's request a lot of attention for the physical world. Let's say like when people are driving, like people are already put a lot of attention into the physical world. Like how do you see people like the adaptive mixed reality system could help in that kind of scenario? So yeah.
Okay, so if we have to think about driving, okay, that's a very good question. So first we have to make, I think, two divides. Like first, if we think of the future of driving, where probably we are moving more and more towards automated driving, I see that the support here, like either it's for entertainment, so like VR or AR can be mostly used for entertainment because we are busy, or even for work, but like it's not driving task related, or I think can be used again for recall our attention. So as today, for example, we can have sound auditory notifications. Similarly, we should use virtual notification if we have a VR headset to basically reconnect and redirect our attention to the real world. For example, let's say that there is a takeover request from the car, so that we want to be more to relocate our attention. I believe also that virtual information or digital information can also be embedded, for example, on the windshield of the car to, for example, provide us navigational cues, navigational aids, or display the state of the car. So, for example, the speed, or I don't know, the outside and inside temperature. But I think that the most critical point is to kind of use virtual, but can also be like also not only visual, but also auditory. So to redirect the attention of the user to, so basically to maintain the situational awareness of the scene, especially when we are disengaged with the driving scene or the driving task.
Thank you.
Yeah, thank you.
Yeah, thank you. Yeah, so João.
João?
Yeah. Thank you. Thanks so much, Francesco. It's really nice talk. Actually, a big fan of your research. Previously, I published one paper based on your adaptive VR system. You proposed a algorithm there based on the GSR sensor. Yeah. So I actually have two questions. One is about the adaptive VR system. So while you implementing the physiological sensor-based adaptive VR system, how to control the, or like when the physiological sensor changes, then it might cause frequently adaptation in the system. This might also influence users' experience, right? Could you have any suggestions on how to manipulate or control that part?
So basically you mean that the physiological data or the user is adapting to the change?
Yeah.
So yeah, that's, I mean, okay, that's a very good question. And I believe that I don't address this problem in this experiment. The way to do this, I think, it's to have basically a random adaptation. I think, so basically, because in this way, so here I have two logic, let's say, no? I want to make you feel more kind of focus on the external environment or more your internal information, right? So if you have random adaptation here, so they are going either up or down. I mean, in this case, of course, it depends on the scenario. So that's why rule-based sometimes is limited. If you have a random condition, then you basically, and you can use it as a baseline, then you can actually see the real effect of what you are adapting for. Because it can also be, as you said, the reaction is just reacting to a change, not reacting to the direction of the change. So this is something that a sort of, I mean, you can call it placebo or control as you like, but I think it's something that has to be added when you're doing an experiment as a sort of benchmark, main benchmark. Yeah.
Yeah. So, but actually, personally, I also tried happy and baseline, and when the user's physiological state increase compared to the baseline, and then do a adaptation one, and when the physiological state decrease, then do another adaptation. But you know, like for some of the participants, you will find their physiological sensor might never change compared to the baseline. Yeah. So that's really
in this case, I think that, I mean, at the beginning, like that's what we did here as well, could make sense to have a resting state. So basically, you know what it's happening by default. So ideally, everything that it's happening from the participant is due to what they're actually experiencing in the environment or in the task, whatever. So basically, in this experiment, we actually removed the baseline from the adaptive system. So basically, we were ensuring that everything was event related in a sense. But those are all, I think, all things that have to be tested before, at least in a and then, I mean, there's always the chance that for someone it doesn't work. I mean, this also applies to technologies that are not only based on your body, right? Like for some people, like the dictionary in the phone, it's a bit weird, or like they make errors as well. So, and this I believe can be actually tackled a bit when we are actually moving to more automated approach. So basically, if you have, for example, a high collection of data from the participant, then you can basically train a user-dependent model that is basically extremely sensitive to the change only in that user. This is to a certain degree is limited because it doesn't work for everyone, but with the idea of having an application, then it makes sense, because at the end also the keyboard on your phone is actually based on your tapping. It's trained on millions of users, but it's the training data and the validation data are based on your tapping.
Okay, thank you. And another question, sorry, I have one last question is about the integrated sensor into the VR controllers. So you know, like the sensors could be very sensitive to users' the head movement or even sweating state, and sometimes like if you the force you apply to the controller might also influence the signal quality, right? So, yeah. So how do you address that? Like special noises in the signals.
I mean, noise in the signal. I mean, there are many ways. Like depends on the purpose. So like, and I believe like in an experiment you can, for example, like control, like you try to have condition where they're mostly sitting, for example, and things like that. Our idea here, it was that we wanted to have artifacts because we wanted to evaluate how the signal behaves. In general, to control for artifacts, I think like there are some pipelines that can basically account for the movement. So basically, if you add gyroscope or accelerometer data, you can actually identify the time points where a movement was done and with which speed. So you can basically identify the noise there. And you can, for example, also train a machine learning model to automatically detect the motion artifacts in this sense. For the let's say thermal artifacts, like I don't know, because they are sweating because of the temperature, we actually placed the electrodes here on parts of the fingers, like specifically here, and those areas are mostly sensible to your emotional arousal. So if you're sweating here, it's because you're more activated. There are other areas like more at the bottom of the hand, or also like, I mean, of course, here on the head. So it is like you can counteract a bit the thermal artifacts with the sensor positioning. But then like I believe that to a certain degree, we need to accept that there is noise, that is the signal we're using, and there is nothing we can do. So automated artifact detection, I think it's the way to go but this requires a lot of training data. But again,
Template
thank you
matching.
so much.
Yeah, kind of like template matching. Thanks, Francesco. Yeah, this noise in this question comes to every physiology researcher, how to remove the motion out of head.
I really
We are
had this
used to-
question, billion times, yes.
Yeah. But thanks for the feedback. But I have a follow-up question on Zhuang's first question. So so how do you ensure that the adaptive systems remain intuitive and non-intrusive for users while optimizing their experience? So because adaptation with physiology can vary, and how do we sort of think of designing those kind of systems that can just
I think that's a very good question. I mean, and I think it applies to adaptive, like everything that is kind of like basically how do we handle the fact that sometimes changes are going against our expectation, basically. Like let's say I'm very engaged with you and I'm talking with you, and for example, the adaptive system wants to fade away all the Zoom participants, and then this can also annoy me. I think that those things can actually be integrated also with physiological data. So for example, when an event goes against our expectation, or we perceive that we made an error, for example, there are event-related potential. So again, information that is coming from the brain that basically shows us that something is unexpected and not disliked, but perceived as something that goes against our expectations. Then you can fine tune. So for example, you can basically integrate an evaluation of the adaptation, so that it's like you can say expected versus not expected. And of course, if it's not expected, you can still reverse. Then this can also open a new conversation. It could be like, something still unexpected can still be good for you. But this, I believe, can actually be evaluated and either change or not, depending on the scenario.
So basically, adaptation will also have like a feedback thing, but based on the metrics that the cognitive load. Yeah, thank you.
Yeah,
that's interesting. So I have one more question, which I've kept for this empathic computing and beyond series. So if anyone else have any question, Mark, do you have any question? Or
no, I just want to maybe this is the right time to do it, but I want to let people on the line know that we have an empathic computing journal, and so some of you are interested, maybe want to find about it. Can you let me share my screen? I'll show people the link. And so well, Francesco and others in this group, or other people, it's maybe a good venue to publish your research. This is the page here, and I'll put into the chat as well. It's just starting, so I'm the editor-in-chief, and we're looking for new submissions. So if anybody online wants to submit, and I think because it's just starting, it's open access journal, but the fees are waived, and for the first 15 or 20 publications or something like this one. So it's a good opportunity to get your empathic computing related publications out into a journal. So anyway, I'll stop my sharing there, and I'll let you wrap up as well.
No, thank you, Mark. I mean, thank you. The last question was actually around the same, like the empathic computing. So, Francesco, given your work in like adaptive mixed reality system and understanding human behavior through physiological signals, so how do you interpret empathic computing? Just what do you think about empathic computing, and how does it influence your research?
I believe, I mean, empathic computing is basically, I mean, to my understanding, is also like a way, like an alignment between the interface, the system, the technology, and the human. And this basically means that like there is a complete, I mean, it's more than adding intelligence. It's a way to, you know, empathic. So understand, putting yourself in the state of the other, or in the state of the user in this case. So I believe it's like probably the next way to see intelligent computing, intelligent interfaces. So it's probably also adding not only the attention, cognitive, or performance lens, but also adding a emotional and an arousal. So it's basically putting the, let's say, cold and warm cognition together. So I think it's an add-on to intelligent interfaces. So yeah, it's something that we have to consider and we have to integrate more and more as well. Yeah.
Wonderful. Wonderful. Thank you. Thank you. I mean, yeah, that's just one. I'm collecting perspectives from all the, you know, speakers. What do they think about and how does it influence your research? So I'm sure in future we'll have more sort of, you know, collaboration, because your attention and those like cognitive load part is essential for the cognitive part of it. And our lab also works on the emotion part. So definitely we are looking into future collaborations. Thank you. Anyone else have any question? No? Well, yeah, if we don't have any question, I would like everyone to thank Francesco for staying up late. I'm sure it'll be like 11 or 12 or maybe late in the night.
So it's hilarious. It's okay. I'm an old sometimes. I stay awake.
Wonderful. Thank you very much.
Thank you so much. That was really great.
Thanks everyone.
Thank you.
And
Thank
yeah,
you,
I hope
Francesco.
we can. Yeah, I think like feel free like to, I mean, contact me like through emails or I don't know, LinkedIn, whatever. Like I'm very happy to, even just for having a, let's say, a research chat, but also for potential collaboration. Like I'm happy to well, share my knowledge, and also if all of the materials that I have in my research, in my papers, are actually openly available. So if you want to have a look at them, or if you have questions about them, feel free to reach out. Like I'm very happy to keep the conversation going. I think it's super important, and your lab is central in this. So I'm also grateful to you for my research, because I mean, without the building up on each other's research step, it wouldn't be possible. Thank you.
Yeah, I still remember our conversations.
Are you going to be at the IEEE VR conference in France in a month?
Maybe like we were planning to submit a couple of things like as a LBW, but it could be something that we can go. Maybe just for attending. We didn't submit because, of course, this year the deadlines with Kai were a bit of an unfortunate match, so we tried to prioritize Kai, but
of course, yeah, definitely. Well, maybe we'll see each other then. It'll be great to see you. So
yeah, it would be very nice. Yeah, I agree.
Great. Okay. Good.
Thank you very much.
Great.
Yep,
Thank you very much.
Thanks to everyone.
Thank
you. Thank you.
Yeah.
Have a good night and rest.
You have a good day. Enjoy the New Zealand summer. Yeah,
you should come. You should come.
I should.
Yeah.
Let's talk soon, Kunal, and thank you everyone for coming as well.
Bye-bye.
Bye-bye.
Thank you. Bye.
Bye.